So this lesson is on the ideal gas law, which is essentially another equation to describe various conditions of gases, such as pressure, volume, moles, and temperature. So it is similar to some of the other gas laws that we learned in previous lessons, like Boyle's law, Charles's law, or Gay-Lussac's law. Except that while these laws right here look at like the pressure and volume at one state and then the pressure and volume at a different state, this is just the pressure, volume, moles, and temperature at one in one instance, or so at one state. So this doesn't look at like a change in pressure or a change in volume or a change in temperature as we had seen in some of these other ones, right? The fact that you have N1, T1, or N2, and T2 means that the moles or temperature is changing. This has no change in pressure, volume, moles, or temperature. So this right here, R, is a new concept that you haven't seen previously, and what it is the universal gas constant. And it's part of this equation, and it allows this equation to exist because it is a constant of proportionality. So R is the universal gas constant, and effectively all you need to know is that these are the values for R, and you'll see that they are different, but that's because this is the R value if pressure is in kilopascals. Excuse me, and this is the R value if pressure is in atmospheres, and this is the R value if pressure is in torrs. So when you use the ideal gas law, you have to look at what the units of pressure are and then use the correct universal gas constant. Note that the units of R are in also liters, right? So that means that volume always has to be in liters and temperature always has to be in Kelvin. And that's something that we have seen before. So choose the R value with pressure units that match your data. So we'll jump into the first example, which is determine the pressure of 5 liter container at 40 degrees Celsius if it contains 4 grams of helium. So what I'm going to do is I'm going to take what I have in this question, so P, V, N, R, and T. So pressure I don't know, right? And it's asking for it in torrs, so we're going to find out what the pressure is. We have 5 liters, so that's the volume. It's a 5-liter container. Moles, we don't have. However, we do have 4 grams of helium, so we can take 4 grams of helium and then multiply it by its molar mass. And so we see helium right here. We've got 4 grams per liter, right? So then we say 1 mole, 4 grams, I said 4 grams per liter, 4 grams per mole. So 1 mole of helium is 4 grams. Okay, and we'll see that that just means that we have a mole of helium. The R value. And for this data, because it's in torr, we have to use this value right here. So we say 62.4. And then torr, liters over moles, Kelvin. It can be a bit challenging to write this all out. So, you might eventually will just omit the units. And then temperature is 40 degrees Celsius, but plus 273, so that's 313 Kelvin. Okay. And then we can go ahead and use the equation. So PV is equal to nRT. I want pressure, so I'm going to divide both sides by volume. That'll allow volume to cancel there. And then I have pressure is equal to nRT over V. And so pressure is equal to, I have N is 1 mole. So 1, my R value is 62.4. My temperature is 313. And V is 5. So putting that into my calculator, 62.4 times 313 divided by 5. I didn't have to multiply by 1 because it's a waste of a keystroke. So we end up with 3,906.24. So 3,906.24 And then that is the answer in torrs. Now, if we take a look up here, 3 significant digits, 3 significant digits, 3 significant digits, which means that this has to be rounded to 3 significant digits. So I'm going to write this as follows. 3.91 times 10 to the power of 3 torrs. Okay, and that gives me 3 significant digits in scientific notation to allow for 3 significant digits, and the correct units right there. Okay, let's move on. Applications of ideal gas and determine the density of a gas. So just so you're clear, density is equal to mass over volume, right? But the ideal gas law, if we look up here, PV is equal to nRT, or PV is equal to nRT right here. We don't have any mass values in here, but what we do have is we do have moles. So this is what we're going to do. We're going to find N over V, and then we are going to convert to mass over volume using molar mass. So we'll find N over V first, and then we'll convert to mass over volume, because that is what density is. So I'm going to start state my ideal gas law. PV is equal to nRT, but I need to get N over V, right? So the first thing that I'm going to do is I'm going to divide both sides by V. Okay, so that cancels here, and then I'll get P is equal to nRT over V. But the issue here is that we would need N over V so that we can go to M over V using molar mass. But I have RT in the numerator, so what I will do is I will put RT in the denominator here, and if I'm putting it in the denominator there, or if I'm dividing by RT here, I have to divide by RT on this side as well. RT will cancel here, RT will cancel here, and look, I have my equation for N over V right there. Okay? Alright, great. So now what I'm going to do is I'm going to plug in these values. So my pressure is 110 kilopascals. 110 kilopascals. Because it's kilopascals, I'll look up here. My R value is 8.31. So 8.31. And then my temperature is given as 30 degrees Celsius. So that should be 303 Kelvin. And that's equal to N over V. Putting that into my calculator, I get 0.0437, and this will be moles per liter, is equal to N over V, as you can see right here. Now, I'm going to keep all these digits in my calculator. I'm going to round at the end. All right, so I'm going to leave this right here. I'm going to write it as 0.0437, but I'm keeping those in my calculator. Now what I have to do is I have to take this moles per liter and I have to convert it to mass over liters, right? So I take 0.0437 moles per liter, and I'm going to multiply that by the molar mass of acetylene. And the molar mass of acetylene, well, I'll just do that on this side here. So the molar mass of acetylene is equal to 12.01. So that's the molar mass of carbon times 2, plus the molar mass of hydrogen, which is 1.01 times 2. Okay. Plugging this into my calculator, my molar mass for acetylene, C2H2, is 26.04 grams per mole. So then times 26.04 grams of acetylene for every 1 mole of acetylene. Okay, and then we cancel and cancel. And so what I'm going to do is I'm going to take this molar mass that I have right here, 26.04, and I'm going to multiply that by the full value that I had in my calculator previously, and I get 1.1376, but looks like I have 3 significant digits to go with here, so 1.14. 1.14 grams per liter is my density of acetylene gas. Okay, finally, determine the molar mass of a gas from its density. Alright, so know that molar mass is given to us, right, as, look, we can even look over here, grams per mole. So mass over moles. If we look at this question right here, I have mass right here. Okay, so I have mass. Mass is equal to 2.609 grams, but I do not have moles. So I need to find moles in order to get molar mass. So how will I find moles? Well, I can use the ideal gas law. So if I go PV RT, and I'm not going to write N because I have it already up there. The pressure is 0.5 atmospheres. The volume, well, this was grams per liter, right? So if it's grams per liter, that means grams per every 1 liter. This just means 2.609 grams for every 1 liter. So volume is 1 liter. R in this question, because it is in atmospheres, I'm going to have to use atmospheres right up here, 0.0821. That's my R value. And the temperature here is 100 degrees Celsius. So that's 273 plus 100. That's 373 Kelvin. Okay. So if I want to find N, I'm going to go PV is equal to nRT. To get N by itself, I'll divide both sides by RT. So PV over RT is equal to N. And then I'm just going to substitute those values in. Pressure in this question was 0.5. Volume in this question I have is 1 liter. R, I had to use this one, 0.0821, because my pressure was in atmospheres. And temperature is 373. And that's equal to moles. Okay, I'm just going to take a second. I'm going to put that into my calculator. Okay, so this is what I get. I get 0.016327. So this is what I'm going to do. I'm going to put this into my calculator. 0.0163 moles, right, as my N value. But I'm going to keep this in my calculator right here. And one way I can do that with this calculator is I can store, so STO, and I'll store that in my A memory slot, and then I can clear it and recall it later. Molar mass, remember, is mass over moles, right? Mass over moles, so mass over moles. My mass was given as 2.609 grams, and moles is 0.0163 moles, but I'm going to use the value that was in my calculator. So therefore, molar mass is equal to 2.609 divided by, I get 159.79, but I only have 3 significant digits here, 3 significant digits here. I have 4 significant digits here, but I've got the 3 significant digits governs this. So I'm going to end up with 160. 160, I have to put the decimal there to indicate that that 0 is significant, grams per mole. Great, so just these 3 examples are given to you for the lesson today. And the homework is on the next page right here, Ideal Gas Law Practice, and it contains questions that we've seen in the examples. So if you get stuck on any of them, go back, redo the examples, and the answers are given to you right there. Thanks for watching.